Welcome to Oddly Real. I'm Nem Stefanovic. We live in a three-dimensional space that has length, width, and height, and there doesn't seem to be any other spatial direction we can move into. However, that doesn't mean it's not necessarily there, and it doesn't mean that we can't try to understand fourth, fifth, or higher dimensions. Spaces that have more than three dimensions can be referred to as hyperspace. What would a four-dimensional object look like? Our brains can't seem to be able to construct such a visual. Yet, there are techniques that we can use to help us to visualize these strange hyperobjects. In this episode, we'll define some intuitive ideas around dimensions for space and objects, as well as techniques to help visualize higher dimensional shapes. What do we even mean when we say something has a dimension? Let's start with a single point in space. The actual point itself is considered to be zero-dimensional. Even though the point may have a coordinate location somewhere in space, the point itself doesn't possess length, width, or height. If we were to change the coordinate location even slightly to any degree of magnitude, we'd no longer be positioned on the point. We'd be at another point. The point doesn't take up any room in space. In contrast, a line does have a single dimension, length. In order to specify a point on the line, we'd need to use a real number to indicate where along the line the point lies. It requires the use of one coordinate or parameter value, hence one dimension. It doesn't matter how the line is oriented in space, or even if the line is in multidimensional spaces like 3D space. It's still an object that just needs one parameter in order to define the position of any point along the line. It might surprise you that this also extends out to curved lines as well. The reason I say that is if a line curves in some way, that would be spilling out into another dimension of space. However, just like in the case of the line, the extra dimensions around the object don't actually matter for its dimensionality. The thing that does matter is how many parameters we'd need to be able to describe the object. So even a curved line can still be fully defined using just one parameter. For example, a helix can be parameterized as the following. Another interesting example is a circle. A circle is different from a disk, which would include the surface points on the interior. Instead, a circle is just the points on the outside perimeter of the object. Interestingly, the circle is drawn on a plane, which we know is two-dimensional because it has both length and width. However, the points on a circle can be parameterized using only one variable, which again makes it a one-dimensional shape. Of course, if we include the interior of the circle, then we have a disk, which is two-dimensional. Why is this two-dimensional? Because now you need a way to reference the points within the body of the disk. That requires two coordinates, both length and width. We can, of course, generalize this conversation to other objects in higher dimensions, like a cube in 3D space. The cube has length, width, and height. In order to represent any point within the body of the cube, we'll now need three coordinates, and so it is a three-dimensional object. But what about four dimensions or five dimensions in space? The concept of a four or more dimensional space can be referred to as hyperspace. Does hyperspace even make sense to talk about? In our physical world, we traverse space only in three dimensions. We can visualize this more easily by putting rulers along each dimension so that they are perpendicular to each other. We start by adding one ruler, and then we add another ruler that is perpendicular to the first ruler. Finally, we add a third ruler that is perpendicular to the other two. But now we've run out of ways to add more rulers. There doesn't seem to be a way to add a fourth ruler that can be perpendicular to the three other rulers. It turns out that it's actually not too difficult to work in 4, 5, or more dimensions mathematically. We can use the same mathematics in any size dimensional space. In fact, multidimensional spaces are quite useful and used regularly by data scientists. Many data sets will have multiple features in them, such as the demographics of people like age, gender, location, income, marital status. It turns out working in multidimensional hyperspace is not an issue, but trying to visualize hyperspace is very different. We can't seem to visualize 4 or more dimensional objects directly. However, there are techniques that exist that can help give us some intuition about these strange hyperobjects. Let's start by first trying to understand higher dimensional spaces by looking at simpler, lower dimensional scenarios. What if we were living on a 2-dimensional space? How would we see 3 dimensions? A 2-dimensional being would see objects in their space just from the side. So they would see a 2D object, like a circle, as a curved line in 1 dimension. But they would have the context to know that there's a front, a back, and sides to what they're seeing, even though they don't see the front and back at the same time. So they would know that they were looking at a 2D shape, a circle, just by understanding it had depth behind it. Next, let's say a 3D sphere moves through the 2D space. What would the 2D being see? The being would first see a little spot in their view, followed quickly by a growing circle, seemingly out of nowhere. They would see the circle reach a maximum, then start to shrink until it was totally gone. The 3D sphere would look like a circle since they would be viewing a cross-section or slice of the 3D sphere at any given time in their 2D space. What if the 3D object that was passing through the 2D space was something more complicated? Let's say a human being put their hand through the 2D space in front of the 2-dimensional being's eyes. Now, the being would see multiple blobs appear out of nowhere that would grow in size and continuously change shape. They would be the fingers of the hand as they crossed through the space. The 2D being would then see the blobs start merging into one another into a larger single blob. That would be the palm of the hand and then perhaps the wrist, seen as a cross-section within the 2D space. This would look very strange to a 2-dimensional being. Let's try something different. We can unpack a 3D cube, like a cardboard box, to flatten it out into a 2-dimensional object that looks a bit like a cross. Using this technique, the 2D being can again try to understand a higher dimensional object from its components, which are 2D, all unfolded in a 2D space. The 2-dimensional being would see this unfolded box look like a set of squares connected together. But how would the being refold this shape back up into a cube? From the perspective of the 2D being, it can only fold left or right within its space, but there doesn't seem to be a way to fold the boxes that way. Their length and width prevents that from happening. Yet, as 3-dimensional beings ourselves, we see where that fold happens. It's along the lines within the cross that can be folded up into the 3rd dimension. So how would a 4D hypercube look to us unfolded in 3-dimensional space? It turns out it would look like this, a tesseract. Much like the 2D example, the components of this cross-like structure are made up of native shapes found here in 3D, those being the 3D cubic components of the cross. So all we have to do now is fold this back up into the 4th dimension. But if you look closely, the parts that would have to fold up look like flat square areas between the contact points of the boxes. I don't know about you, but I'm definitely struggling to see how those will fold. I'll leave that one with you to meditate over. Let's try another technique to visualize higher dimensional objects. Going back to our 2D space example, we can now try casting a shadow on the 2-dimensional space by holding a light up against a transparent or wireframe cube. The shadow will look something like a square contained within and connected to an outer square. So what happens when we take a 4D hypercube and shine a light through it into 3D space? Well, it looks like a cube contained and connected within another cube. So again, you're welcome to try to visualize how that might relate back to a 4D hypercube. Of course, there are other techniques as well. In the 2D example, we can take a slice of the 3D object, like running a plane through the object in different ways and different angles in an attempt to see slices of the 3D shape. Similarly, we can try that for 4D shapes as well. But try as we might, it's not easy to understand hypershapes outside of our 3D space. I want to cover one more example here that's kind of interesting. There's a special geometric object called a Mobius strip. This looks like a normal strip of 2D material, like paper, that curves around in a circle, but with an added twist along the way. Now, why is this so special? Well, a two-dimensional object will have two sides, like a front and a back on a sheet of paper, or an inner side and an outer side in a normal looped strip. But look closely at the Mobius strip. It actually only has one side. If you trace your finger starting at a spot on the inner strip, it'll twist out to the outer strip, follow along the outside, then twist back into the inner strip and back to the starting point. This all happens without taking your finger off the paper or crossing over the edge. Now, it gets a bit weirder, since if you were to take a two-dimensional being that lives on the strip, they too could travel across the strip through the twists and back. But when they do so, they'll end up being a mirror image of themselves, and all of their organs and body will be completely reversed from left to right. I also want to make one more point about the dimensions of space. We've only talked about higher dimensional finite spaces here, meaning that they consist of a specific number of dimensions, like 4, 5, or 10. But there are also spaces that have infinite dimensions. For example, the space of all polynomial functions is infinite in dimension if we use the powers of x as a base for each dimension. We'll leave it here to let your imagination run wild for a bit. I hope you found this episode interesting, and remember, oddly real, really interesting.